So very good morning to you all. First of all, I would like to thank the organizers of this meeting. I will talk today about foragers, and we will see whether inertia will help the survival of the forager or not. My collaborators in this work are Mohammad Akib Molla, who is my PhD student, and Professor Parunga Mashin. So a forager is basically any living organism which moves from one place to another in search of resource. It may be food, it may be shelter, or something like that. So this is basically we see in animals. We always see such kind of foraging in animals. So when you have something dropped on your kitchen floor, you will always see a line of ants will come to collect their part from that. And we will see that bees are having a nest at somewhere, and they will move to some other place to form their nest and something like that. And you will see underwater animals also move from one place to another in search of their resource. And I will show you here a picture. This one is a tiger cub from Tadoba. And you can easily see that saliva is dropping from its mouth because it has heard a sambar deer's call. It will soon move to hunt it. And this is what tigers will do. They also stays at some place for some time, then they move to some other place. This is also in search of resource in sometimes, and there may be another reasons. So this is common in animals. This is also found in human beings nowadays. A group of people who are nomads, they move from one place to another in search of resource. And this actually has started from ancient times, where this one is a famous picture from a paper by O. Stephen. This is published in Philosophical Transactions of the Royal Society B, where we can see that peopling of continents and islands that all started from Africa, and this is also in search of resource, mainly food and shelter. So the thing is found in any micro or macro organism, living organism, and this may be there may be some kind of stochastically driven processes. There may be some physiological processes also, and so this is quite common. And in every case, the main motivation is basically to optimize the searching time for the resource, and it will ultimately help the forager to increase its lifetime, and we will see that whether it's true or not. And this is basically the motivation behind our work, that whether this kind of amount of food available and its movement is some way related. And here we have introduced a particular parameter, which is inertia. I am coming to that. So basically our system is a 1D or 2D random walker, and we have associated a starvation time initially for every such worker, and that is basically whether it will have some food for some time. It can continue with that, it can continue its movement with that for some S number of time steps. That is we are calling the starvation time. And whether it is on a full site, I mean the sites which are filled with food morsels, whether it will consume the food completely and then it will move on. The main factor added in our work is inertia, that is the resting probability. So when it will take food at a moment, it will relax. I mean it has food, so it will relax. That is we are calling inertia. So we have associated a probability, and that we are calling the inertia P. Now this is basically some pictorial representation of that. So suppose the worker is here at the beginning, and all the sites are filled with food. It will be here at the beginning, and it will rest. It will consume the food there. It will rest with probability P, and it may move with probability 1 minus P on either side of that particular point. So suppose it is moving towards left, then what happens? It will go there and take the food morsel from there, and again it will rest with probability P or move with probability 1 minus P, and suppose it is moving towards left again. So in this way it will continue. The same I have shown on a 2D lattice. So suppose the worker starts from this point, and it will come to here with the food morsels. It has eaten all the food morsels, and after that, suppose it will move from this point to here. It has actually 4 points to go, but it will suppose moving towards the right, and in that case it will find no food there. So if its starvation time is 3, it will continue suppose from here to here and then here, and it will ultimately die because it will not find food for 3 steps continuously. So this is basically our model. So here is a brief algorithm. All sites are filled with food morsels, and it will start from a site, it will consume the food there, and it will take rest for some with some probability, or it will move. And if finally it reaches some site where it will find no food, and ultimately it will have X successive steps like this, it will ultimately die. So S is the starvation time, and the forager's lifetime is tau. So this is a picture with no inertia. I mean, it's a space-time diagram, and you can see here the clear space is basically the forager eats the food, and it is basically having some food morsels are it has been eaten, and therefore this part is becoming a desert in this way. So the forager will ultimately, after a certain time, it will die. So here are the results from our paper. So it's basically the number of distinct sites visited by the worker with time, and the p equal to 0 case is the original case where it has no inertia, and we can see that it has for other values of p, I mean when inertia is increased, we can see that the average number of distinct sites is low for lower s. The same type of things can be seen for 2D. The only exception is for 1D case, the s xi was 0.5, I mean square root of s, and here xi is 1. This is the exception. Now it's the most interesting result is the lifetime, about the lifetime. When there is no inertia, you can see it is going like s to the power 1, and this for any other p, for higher values of inertia, what happens is you can see after a certain value of s, its lifetime is actually increased with higher inertia. So this is an interesting result, because in some case, if it can optimize the inertia and its movement, in that case it can survive for longer. This is for the 2D case. The same type of behavior can be seen. I am not going into this. This is something we have from the previous 2 graphs. I am not going into this. So finally, we have tried some analytical treatment of this one also. I am skipping the details, but we have tried a diffusion equation. So when all the sites are filled, it will move like a lazy worker. But as time goes on, it will try to, there will be less number of food morsels, and somewhat in some sense, it will not be exactly like a lazy worker. So its p is modified, and we have associated a factor, a function pt, which will be 1 when the worker or forager starts, and it will ultimately, the function pt will ultimately decrease with time. So in this way, we have obtained a distribution of Pn, the average number of distinct sites, distribution of that. This is somewhat what we have, and this matches exactly with the p equal to 0 case. We checked that, and this is the p equal to 0 case in paper of Redner. So we checked that, and here is our simulation results for different p's, and this is the analytical result for different p. So it quite similar, and what we actually want to conclude is there are several other results also, like relaxation time. We have tried some other models for the same also, but the main thing we want to conclude here is the survival time can be optimized with inertia. If it actually controls its movement with inertia, its survival time can be increased. So that's the main conclusion, and so thank you for your attention.
Now we have time for questions.
Yeah. Yes. This is actually the modified diffusion constant. It's time dependent. Yeah. What? Step size is one. Yeah, yeah. Step size is one. I mean, there are 1D lattices. They are spaced equal space. Oh, actually, in this is kind of continuous version of that. When we did the simulation, there are lattice grids, and from that we tried this. So it's a lattice spacing. I probably cannot understand your question.
So this is just a question I came into my mind. How is P related to the inertia? I didn't get that.
P is basically a resting probability. So when the forager is consuming food, it will rest with probability P, and it will move with probability 1 minus P. So it's kind of, its motion is somewhat restricted. That is what we are calling inertia here.
Just one question here. So can this model be, tested or with the migrant workers?
Migrant workers.
Yeah.
Yeah, we may try. The same thing can be used with some other features, has to be incorporated there also. Yeah.
So here the survival, when migrant workers go from one place to another, and then how long they spend there, what is the money that they get, and which you can.
But there is actually there is some other cause for which they go, and they are actually not. There may be some other factors associated. What I mean, yeah. But that can be. It's a good suggestion. I mean, that can be checked. Yeah.
Okay. Thank you.
Okay, so let's thank our speaker.